What does it mean to have a 95% confidence interval? Well, a 95% confidence interval is an interval of estimates of a parameter. There's a true number, for instance, the true median income for San Francisco City employees, and we hope that our interval is going to contain this number. Our interval is constructed based on random sampling, and 95% is called the confidence level. 95 could be replaced by any percent between 0 and 100. A higher level means wider intervals, because we need to be more confident, we need to have a bigger interval that has a higher possibility of containing the parameter value. The confidence that we're talking about is the confidence in the process that generates the interval. If we call an interval good if it contains the parameter, then a 95% confidence interval is produced using a process that should generate good intervals about 95% of the time. In a moment, we'll go to a Python notebook to show an example of this, but for now, let's just look at a graphic that Python notebook will produce. In this graphic, I've computed 100 different 95% confidence intervals for the median income for San Francisco City employees. The median income is represented by this red line right at about $107,000. The 95% confidence intervals are each stacked one on top of another like plates, slightly offset, and those intervals contain the red line about 95% of the time. Close to 95% of these confidence intervals contain the true parameter, which is what we would expect. Here's some code that runs a huge simulation. It can take a long time. What we're going to do is produce 100 different 95% confidence intervals, all from the same original sample of 300 employees from San Francisco. After you've done this, you could run the cell below in order to produce the graphic that we just saw before. We expect about 95% of these 100 intervals to contain the true population parameter, that is, the true median income for the San Francisco employees. Here's a table that we could make consisting of the left and right endpoints of the 100 different 95% confidence intervals, and we could call good the number of intervals that contain the true parameter, and then we could find the proportion of those good confidence intervals. And it turns out that in this simulation, we got 93% of our confidence intervals containing the true parameter. And 93% is very close to 95%. That's the sense in which we mean that we have 95% confidence in these intervals. It means that 95% of the time, the interval that's produced will contain the true population parameter. It's important to use confidence intervals appropriately. Let's test your knowledge. Suppose we're looking at a collection of mothers that are giving birth in a hospital, and we take a sample of those mothers and compute a 95% confidence interval for the average age of the mothers in the population. Suppose we find that our 95% confidence interval is 26.9 to 27.6 years. Is the following true or false? About 95% of the mothers in the population were between 26.9 years and 27.6 years old. Answer this question on your own and then check your answer on the next slide. This is false. We're estimating that their average age is in this interval, not that 95% of the mothers are in this interval. Let's try another one. Is this what a confidence interval means? An approximate 95% confidence interval for the average age of the mothers in the population is 26.9 to 27.6 years. Accept that as a given. Now, is the following statement true or false? There's a 95% probability that the average age of mothers in the population is in the range 26.9 to 27.6 years. Answer this question on your own, and then check your answer in the next slide. No, this also is false. About 95% of the intervals produced by this process will contain the population average, but any particular interval either does or does not contain the population average. There's no probability that we should be talking about here. There's a bunch of situations where we shouldn't use the bootstrap. If you're trying to estimate very high or very low percentiles, or the maximum or the minimum, then you shouldn't use the bootstrap. Also, if you're trying to estimate any parameter that's greatly affected by rare elements in the population, then you should avoid using the bootstrap. The bootstrap is best used when the probability distribution of your statistic is roughly bell-shaped. And if that's not the case, then you should avoid using the bootstrap. You can check this by checking the shape of the empirical histogram for your sample. If that sample is roughly bell-shaped, then you're probably in good shape to use the bootstrap. If the original sample is very, very small, you should also avoid using the bootstrap.